open the learning summary. Let me just check that we're live. Check that we're live. Should be live. Nope. Nope. Okay, no sign that we are live. Okay, it looks like we are live. Looks like we are live, guys. Okay, it looks like we are live. Let's keep going. Add more tags. Yeah, we could definitely add more tags. Okay, summary. Let's go to summary. Let's keep going. No need. Summary. 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 Okay, summary, summary, summary. Let's go to the summary, and then we have a reading. Rachel reading. All right, let's try and make it big. There we go. Okay, let's get back on the wagon. Let's get back at it, guys. Back at it. Trying to do the speedrun. Okay, summary. In this video, you learned that graph databases store information in entities and databases and relationships. Graph databases store information in entities and relationships. Okay, let's keep going. Next one is graph databases are impressive when your data set resembles a graph-like structure. Graph databases are impressive in your data set when your data set resembles a graph-like structure. Okay, graph databases don't shard well, but are ACID transaction compliant. A unique feature. Graph databases don't shard well, but are ACID transaction compliant. Okay, excellent. So what's the next page? Course 10, week 1, module 1. The primary use cases for graph databases are for highly connected and related data, for social networking sites, for routing, spatial and map applications, and for recommendation engines. The primary use cases for graph databases. Primary use cases for graph databases are for highly connected and related data, for social networking, for social networking sites, for routing, spatial and map applications, and for recommendation engines. All right, pretty gnarly. So that's the summary. We're just going to quickly go over it, and then we'll leave it there. So this is the summary for NoSQL NoSQL categories graph, questions, learning objectives. So this is NoSQL graph category that we're going over. It's just a type of NoSQL database. Okay. Summary. Graph databases store information, entities, and relationships. So basically, they like tables. They're very similar to NoSQL, but they're like a novelty act. They're not actually like a SQL tables. They're just a wannabe, essentially. Graph databases are impressive when your dataset resembles a graph-like structure, which means you have your relationships as edges and your nodes as your entities as your tables, and they're all related. For example, such as social networking, routing, spatial, map, and recommendation engines. Graph databases don't shard well, but are ACID transaction compliant. Because of the relations, they're very similar to relational database management tables, so therefore they are ACID compliant, atomic, consistent, isolated, and durable, and they do shard well. All right, there's one more. So sharding basically means put on a whole bunch of servers and a cluster of servers which then have nodes, which just have partitions, and so on and so forth, which can be accessed by clients. Well, essentially the nodes are the servers, but yeah, nodes, just a cluster of nodes is a cluster of servers, so same thing. The primary use cases for graph databases are for highly connected and related data. So as we say, tables which have primary keys, related stuff, that is for graph databases. For social networking, sites for routing, spatial and map applications, and for recommendation engines. So for recommendation engines as well, because it's all related to the same thing. Map applications relate to the same specific topic, and spatial and routing. Let's keep going. So that is that. Now we do a reading. Oh, is this not recorded as done? Hang on. Okay. All right, let's move on to summary and highlights. Sorry, this is the wrong thing. Databases and deployment options. Okay, here we go. Database deployment options. Database deployment options. Okay, so we have three topics here: do-it-yourself, hosted, and DBAS. Okay, so DBAS is this one. This one is hosted, and this is do-it-yourself. Okay, so let's look at this. This is a reading, by the way, so let's just keep that lowbrow and understood. So I'd summarize the three categories. Okay, well, first off, I would say four categories, sorry. First category, key value. So first category, key value. To summarize it, I would say, okay, least complex, value opaque, blah, this is like. However, it is not as atomic. In fact, all of them except for graph are not ACID compliant, and all of them do shard well, except for graph. Essentially, those are very similar. So for key value, you would say like shopping carts and like web applications. Let's move on to the next one. So we have document. So document, essentially, because it's distributed, it's very easy. It's horizontally scalable. As it's very similar, they all are horizontally scalable, essentially. However, single documents cannot be queried and indexed as easy. So there you go. It is unsuitable for data is naturally normalized. So the data, if the data is normalized, essentially relationships, you need RDBMS. And also, if you have multiple documents, you need RDBMS because to link them. However, for documents, they can be used for event logging, absent processing, even instances represent a new document, online blogs, issued comments like operational data sets like metadata for web and mobile apps, documents with the internet in mind, such as JSON, RESTful APIs, and unstructured data. So essentially, some examples of documents would be IBM Cloud and CouchDB, JSH, RavenDB, OrangeDB, MongoDB. So that's some documents. So the documents are pretty chill. Value key value is pretty chill. And then of course we have column. Column seems to me like to make the most sense, right? Because you can essentially, yeah, it makes the most sense for a NoSQL, for a non-relational. So for columns, you can spawn data from Google, you store data in columns, you have column families linked to a key. You can share all sorts of subsets, and you can have the rows part of other columns, and essentially. So it is useful because you can store it on many different servers as well. Counters, column data can be used for logging in events. Column databases can handle being requested as a server. So columns are just the best. This is why Cassandra NoSQL example. Cassandra is the columns, and it handles. It doesn't have for ACID. It doesn't work because there's just the columns are not atomic. There's not related proper relations, and early development queries can be costly because it takes numerous amounts of columns to link together. But you don't essentially have a table or an overall arching view. So the schema is not quite there. Graph, however, a database to store information, entities, and transactions compliant like other NoSQL characters just discussed. Most nodes are highly connected and related. This is for social networking, routing, and recommendation engines. I just want to say like it's streaming or something. No, all the other ones are for streaming as well. But these ones are more specific. So this is for specific cases where they're highly interconnected. The other ones, of course, yes, you can do event streaming like blogs, posts, likes, and whatever. Right, database deployment options. Let's move on to our next item, guys. So this is the reading database deployment options. All right, let's go to database deployment options. All right. This reading introduces the concept of database as a service, and enables you to differentiate between available database hosting options. A major consideration when choosing the best database of applications and organization is around where to host it and how it is being managed. It is important to understand all of the components to make sure you end up with the simplest and most cost-effective option. In traditional in-house do-it-yourself scenario, you will own the setup of the underlying hardware and operating system, installation, configuration of the chosen database management system, overall administration, including patching and support, and of course how the application is. Okay, so okay, so this is do-it-yourself. Okay, so do-it-yourself. Have it on the side. Okay, I have it on the side. Okay, hang on. So this is do-it-yourself. Let's look at do-it-yourself. So do-it-yourself, Okay, do-it-yourself, and essentially we have how many blocks? We have one for design, we have one for admin, we have one for software. So we have 4 blocks. 1, 2, 3, 4. So we have, what do we have? We have, what is first? Hardware is first? Oh no, design. You're in charge of design, you're in charge of admin, you're in charge of software, and you're in charge of hardware. Basically, you're in charge of a lot of things. Okay. Okay, so do it yourself. Enables you to differentiate the available database hosting options. Okay, the major consideration when choosing the database is around where to host it and where it is being managed, to make sure you end up with the simplest and most cost-effective option. In a house do-it-yourself scenario, you will own the setup of the underlying hardware and operating system. So essentially, installation and configuration of the chosen database management system, overall administration including patching and support, and of course how the application is designed. Should we just write this out? In traditional in-house do-it-yourself scenario, you own, okay. In a traditional do it yourself scenario, you will, I'll say we will own the setup of the underlying hardware and operating system installation and configuration of the chosen database management system overall administration patching and support including patching and support, and of course how the application data is designed and how the application data is designed. Okay, there it is, the do-it-yourself one. So I should probably have some comments on it, right? Yeah, let's have some comments on it. Why not? Let's have some comments. Okay, comments on do-it-yourself database deployment option. Come on. Okay, so let's see. In a traditional do-it-yourself scenario, we will own setup of the underlying hardware, operating system, installation, configuration, chosen database. So you will own the system. Let's say nodes because comments is wrong. Own the system. As far as I see here, you will own the system, installation, configuration, chosen database management system, overall administration, including patching and support, and okay, so you will own the setup of the hardware, operating system, installation and configuration of the chosen database management system. Own the you will own the setup of hardware. We will be in charge of DBA. And what else? In charge of patching, help desk, and how application data is designed. That I think comes into the category of the. Alright, so there we go. That is my answer, my notes, and that. So there we go. Putting in the work for you guys. Putting in the work, indeed. Let's move on to the next one, which is the do-it-yourself. Oh, sorry, not do-it-yourself. This is different. This is the hosted. Hosted is yeah, the software seems to. So it's just 3 of them. So this is different. Wait, it's just 3 of them. It's different. Hey guys, it's different because it's just 3 of them. Okay, design. admin software, so on and so forth. This one is called the hosted. Hosted deployment. The other one is called do-it-yourself deployment, and so on and so forth. Let's keep going. So this is the hosted deployment. In comparison, using sorry, this is wrong. Hang on. Okay, this contrasts a little bit with hosted database solutions. A hosted database solution means the provider is choosing what hardware your database runs on, and they are provisioning it for you. But it is your responsibility to provide and install the software, perform the administrative tasks, and do the design. So at the end of the day, the hosting provider are handing the administrator's keys over to you, and it's really up to your database administrators to keep things scaling and running smoothly. Okay, so hosted, for a hosted database deployment, your hoster, I guess, your hosted database platform chooses the hardware for your database. Anything else? So at the end of the day, the hosting providers are handing the administrative keys and up to you to keep things scaling and running smoothly. Install the software means the provider choosing what hardware runs not provisioning it for you, and perform the administrative tasks. You install the hardware. Perform administrative tasks, like, for example, making your DBAs, make sure your database is running. In the traditional do-it-yourself scenario, we were in the setup of the underlying hardware and operating system installation configuration. So patching and support and how the applicant data is designed. So basically you own everything. So hosted deployment is essentially, so hosted is like, do it yourself is like where you do everything. Make a database, make sure the database is running smoothly. Okay, software is like make sure your database is running smoothly. Is there anything I am missing? To provide and install the software for hosted deployment, we must provide the software. All right, so let's make some comments on it, guys. Let's make some comments. Okay. But should we do it directly underneath? Okay, notes on hosted. Okay, so notes on hosted. Yeah, I'm just gonna do it a bit differently. So what notes are there to have? So hosted removes no hardware. You're in charge of software and DBA issues. So what do you mean like by? So it's like there's something we didn't understand, right? I just got to make an explanation for this. So you're in charge of patching and support, administration you're involved for both, but software is different. Hardware and operating system. So installation of software for the hardware, right? The installation means providing what hardware is install the software. So you install the software. You're in charge of installing software for the database. Charge of installing software for database, and also you're in charge of installing the other stuff. Oh, I messed this one up a bit. Hang on. All right, so essentially do it one by one. I don't know. I feel like it is kind of instructive though. Am I the only one who believes that, guys? Okay, so where were we? This one is just design admin. Oh, sorry, hosted. Wait, what? Oh, the next one is DBAS. Okay, so the next one is actually the one they say is best, right? Next one is the one they say is best, right? So all you have to do is just design your database with DBAS. So actually, do it yourself is possible, but it is a bit bizarre. Like you have to create the hardware for your database. That's a bit, yeah. Like you have to like buy like a storage, like a server or something. You have to buy like a silo or something. Okay, so then we have this one is, of course, guaranteed to work, no guesswork. Smallest risk, and greatest productivity. So apparently this is being marketed to us as the best, unless I am, of course, losing my mind. So this is DBAS. Oh, this is just design. Oh, this is just design. Wait, this is just design. Oh, it's not even DBAS. Forget about DBAS. It's just design. Oh my word. It's just design? Wow, okay, that's savage. DBAS, okay. Alright, so DBAS, in comparison, using a fully managed database as a service, or DBAS, is meant to eliminate the complexity and risk of doing it at all in-house and help development teams get to market faster, scale more smoothly and massively, and provide better performance and availability for end users. The only concern for users of a family-managed DBAS is the design and development of their product. Guaranteed uptime, availability, and scalability are all the result of fully managed DBAS. You mitigate risk by offloading database administration and data layer management issues from your development team, and you ensure that your developers need only concern themselves with what really matters, developing better applications for customers. Okay, so another important issue here. Oh, so you guys want to know if I can complete? I don't know, to be honest. I wish I could know. I wish I could just be like, yeah, I'll just finish this guaranteed day, but yeah, it would be pretty sick. It would be pretty sick if we did finish this whole day. Yeah, finishing week 1 would be a very good start. Yeah, a very good start. Yeah, definitely a very good start. You want to know what week 2 is all about? Okay, I can show you, I think. Okay, so we have week 2 here. So week 2, as you can see, there's some videos. It's an upgraded tool. Some more videos, some more tools, and some standard stuff. And then you want to see what week 3 is? I think week 3 is more intense, right? It's more intense. Yeah, week 3 is intense, right? We sort of went over this, right, yesterday, right? Yeah, week 3 is a bit intense. So I say if we get to week 4, let's see. Week 4, whoa. Week 4. Okay, I say if we get to week 4, yeah, if we get to week 4, I think then we're doing really well. If we get to week 4 before the 27th, I think we're doing really well. We have like how many days? We have 8 days, guys. We have 8 days. So yeah, let's see what we can do. Let's go to week 1. Oh, sorry, week 1. All right, continue. I think if I finish week 1, guys, you know what? Why not continue? I mean, we are building on everything, so it is getting interesting. So let me continue with my database and deployment. Okay, let me get my like here. All right. So database as a service. Where were we? The only concern for you, okay, in comparison, is meant for your company. The rest is really messed up. Only concern is for product guarantee uptime, availability, scale, all levels. Mitigate risk of uploading data from your development team, and you ensure your developers need only concern themselves with remedial edits, developing better applications for your customers. Okay, in the comparison using it's really meant to eliminate the complexity and risk of doing it all in-house and help development teams get to market faster. Scale more smoothly and massively, and provide better performance and availability for end users. So what they're essentially saying, what are they saying here, guys? So they're saying eliminate complexity of doing it all in-house and making it get to market faster. So they want to get it to market faster. So they want to get it sold and like on App Store really quickly. You can scale more smoothly and massively because of course you have more data, and you can provide better information, performance, and availability for end users. So, okay, so basically what they're saying is we can get our service to the market quicker. We can scale more massively. Okay, but wait, there's something we eliminate the complexity. We eliminate the complexity and risk of doing it all on our own. Sounds like a lot of fun to do it on your own to me then. So let's keep going. Scale more smoothly. I don't know what they mean by scale more smoothly. Is it because you can put in more time and effort? Because you can, because we can, need to here, put in more time and effort. Because we can put in more time and effort. Oh wait, time and more effort. Our database scales more smoothly. Wait, what do you mean? To eliminate the complexity and risk of doing it all in-house and help development teams get to market faster. I think this is the same though. I think they also scale the same. Easier to benefit. Let's just get rid of this. Let me just write it properly. Easier to reap benefits from easier to reap benefits from high scalability, from scalability, high availability, and what is it? High from scalability and optimum performance, which of course comes with a NoSQL database. Okay, so let me make some notes. What notes will I say about this? Eliminates the design, eliminates the admin. Oh, sorry, eliminates the admin, eliminates the software, and eliminates the hardware. I think that's just my notes on it, really. I mean, I don't know what else they want me to say, but oh, there's more. Oh, wait, there's more. Hang on. The only concern for users of a fully managed service is the design and development of their product. Guaranteed uptime and scalability all result. You can mitigate the risk of overflowing database administration, data layer management issues from your development team, and you ensure that developers only consider what really matters, developing better applications for the customers. You can mitigate risk by offloading database administrators and data layer management issues from your okay. There is no development team, as far as I see. There is no development team or administration that you need to do. Less risk, I suppose. Less risk. And only real concern for us as a user of DBAS is the development of applications. We would assume those must be databases. Well, applications for databases. I'm assuming we can. But there's no admin, there's no software, there's no hardware. It's just you designing stuff. Is there some advantages? I probably would say there is. There probably are quite a few advantages, maybe, but few and far between. I don't know if they're few and far between, but I definitely would do it. I think I'd definitely start with DBAS, but then I'll go to then I'll work my way up to do it yourself. Because do it yourself just sounds so sick. Like you have your own management, like you create the management, you do everything. Obviously, I'd have to buy like a huge supercomputer or what is it, a server? They say like the servers you see in those, huge server to store my stuff in, store my data in, and then I would deploy it. Getting cloud distributed architecture in the cloud, I think that's I don't actually know how to design it because I don't know this. I don't really know the cloud architecture. Does seem it's all managed on a distributed network of servers, but they are not sort of anyway. Okay, so we have do-it-yourself deployment, scenario, installation, configuration of database system administration, patching, and support. So basically, you're in charge of everything. You need to have like contact. People need to contact you for help. You're in charge for support, patching. You have to do updates. Also, installation and configuration of trusted database. You also have doing it yourself scenario. And you have basically everything is do it yourself. So you design, admin, software, and hardware, and you own the setup of the hardware. You are in charge of the database administration, the patches, and support. So essentially, you're in charge of, doing everything for the. Okay, so how would I make sense of this? Again, yeah, you always got to ask yourself, how would I make sense of this? So, okay, do-it-yourself deployment summary. Okay, so you, as a do-it-yourself, you basically have to start up from the hardware. You have to create hardware for it, software to install into the hardware. Then you have data administration to be done. You also have to, in regards to hardware, you probably also have to do, for the software, you'd probably, hardware to store it in like somewhere. Then you would have to, like in-house, as they say. In software, you have patches. Admin, you'd probably have your data administrators. You need data administrators. Then design, you have to design your applications. But patches as well, updates, all that good stuff. Okay, so hosted deployment, how to describe hosted. So hosted deployment, okay, so hosted deployment. What makes it unique from do-it-yourself deployment? Let's see. What makes it unique from do-it-yourself deployment? Okay, so there is no hardware, so essentially you are given hardware and then you can install your software on it. So essentially it's not quite in the cloud, but essentially all hosted on a server. So essentially so you install that. It is less management, but there is always a chance for error with the development team. Okay. DBAS, now this is what we say is guaranteed. Okay, so no guesswork, smallest risk, greatest productivity. We get the service of the market quicker. We eliminate the complexity and risk of doing it on our own. Okay, so you get it to the market quicker, you eliminate the risk. Okay, easier to reap benefits from scalability, high availability, and optimum performance. Elimination. Eliminates admin to software and hardware. There is no development team or administrator that you need to do with. Only real concern for us is the user. Only real concern is the development of applications. So how would I describe DBAS? So I would say, it's less risky because you don't have to have a development team. There is guesswork because. Okay, wait, why would there be no guesswork? There is no guesswork because... Okay, wait, so wait, there's no guesswork because you don't have to worry about like a million things, like keeping track of patches of software, having contact for people for support, like providing information to other people, documentation or something. So, so what about else about DBS? Is there anything you need? Okay, so obviously you don't have design, admin, and that, and so it seems like all you focus on is developing applications. So you can take the benefits of scalability and high availability of performance from the deployment database you choose. Okay, so that is DBAS. I think that summarizes it, guys. Okay, next item. So this is summary and highlights. So this is summary and highlights. Okay. Okay, next item is summary and highlights. All right, this is pretty good. Let's keep going. All right, summary and highlights. All right, let's keep going. Summary and highlights. Congratulations, you have completed this lesson. At this point in the course, no SQL means not only SQL, means not only SQL. NoSQL databases have their roots in the open source community. NoSQL databases have their roots in the open source community. Okay, next, NoSQL database implementations are technically different from one another. NoSQL database implementations are technically different from one another. That is true, because I mean, implementation and deployment are very similar, so, but I mean, if you're talking about database type, then yeah. Okay, well, if it's implementation, it's different. There are several benefits of adopting NoSQL databases. There are several benefits of adopting NoSQL databases, including storing and retrieving session information and logging and event logging for apps. There are several benefits of adopting NoSQL databases, including storing and retrieving session information, storing and retrieving session information, and event logging for apps. Let's keep going. There are four main categories of NoSQL databases: are key value, document, wide column, and graph. The four main categories of NoSQL databases are key value, document, wide column, and graph. All right, very, very nice. All right, let's keep going. Course 10, week 1, module 1. We're about to switch to module 2 very soon. Okay. NoSQL databases have their roots in the open source community. Okay, where were we? Document-based NoSQL databases. Sorry, key value NoSQL databases are the least complex architecturally. Key value databases are the least complex architecturally. Okay, and then we have document-based NoSQL databases. Document-based NoSQL databases use documents to make values visible for queries. Document-based NoSQL databases use documents to make values visible for queries. All right, next. In document-based NoSQL database, each piece of data is considered a document, which is typically stored in either JSON or XML format. In document-based NoSQL databases. Each piece of data is considered a document, which is typically stored in JSON or XML. Okay, XML format. Right, anything more? Column-based databases spawn from the architecture of Google's big table storage system. Column-based databases spawned from the creation of Google's big table storage system. Got it right neatly. Let's keep going. The primary use cases for column-based NoSQL databases are event logging and blogs, counters, and data with expiration values. The primary use cases for column-based NoSQL databases are event logging and blogs, counters, and data with expiration values. Right, let's keep going. Graph databases store information in entities or nodes and relationships or edges. Graph databases store information in entities or nodes and relationships. Speedrun, guys, I gotta keep going. Sure, edges. Okay. Okay, so this serial market is done. Guys. Okay, let's just go over it. Okay, summary and hide. NoSQL means not only SQL. It also means non-relational data. NoSQL databases have their roots in the open source community because the distributed network eventually they had a event, and they called it NoSQL. NoSQL databases are technically different from one another. You get DBAS, so you get do-it-yourself deployment, hosted deployment, and DBAS deployment. Anyway, there are several benefits of adopting NoSQL databases, including storing and retrieving session information, event logging, or two apps. This is too really broad to really. Yeah, that's true. Yeah, so the four main categories of NoSQL databases are key value, document, wide column, and graph. Of course, key value databases are the least complex architecturally, and they don't allow really much for index or queries. They're opaque. Do not support ACID transactions. They are easily sharded though. Document-based NoSQL databases to make values visible for queries. It makes the value visible for queries, so it's not opaque, so it's easier to index. In document-based NoSQL queries, each piece of data is considered a document which is typically stored in JSON or XML formats. In document-based NoSQL databases, so the document stored JSON XML format. Okay, so yeah, each document has JSON, which is basically has columns and keys inside it. That's the sort of source of information. Column-based databases spawned from the creation of Google's big table storage system. Is that true as well? Google column-based databases spawn from creation of Google's big table storage system. I would think so. Okay, yeah, so column-based, okay, they're telling me that. The primary use cases of column-based NoSQL database are event logging. Okay, so for column-based, okay, so column-based, you actually can record specific like events and relate it with keys, but it's not as easy to do as the way otherwise, which is basically tables, which is for graph. Graph databases are store information to entities or nodes and relationships with edges. Very simple. Okay, that is the end of module 1. Now we move on to module 2. Module 2. Okay, so let's mark this as complete. Do we give it a like? Let's give it a like. Okay, let's go to working with distributed data. Working with distributed data. Okay, that is module 2, and our first video is acid versus base. Okay, acid versus base. Right, there we go. Let's keep going. Okay, next we have questions or learning objectives. Okay, let's keep going. Okay, so we've got this. Should we just get some highlight? Wait. Okay, so this is the learning objectives, right? This is the learning objectives, right? Okay, this is learning objectives. Okay, learning objectives. Let's keep going. So, learning objectives. After watching this video, you will be able to define what acid and base stand for. Question 1. Define what acid and base stand for. Okay, next, question 2 is identify the use cases for acid and base modeled systems. Question 2 is identify the use cases for acid and base modeled systems. Okay, question 3, describe the differences between acid and base. Describe the differences between acid and base. Okay. There are our questions. All right, looks like we can start, I think. Okay, but we must sort of label it course 10, week 1, module 2. All right, let's highlight it, the classic highlighting. All right, legendary highlight. Module 2. Module 2. Working with distributed data. Acid versus base. All right, questions or learning objectives. All right, I think we can start, guys. So we just want to answer the question straight away. Well, I guess we could. No, we definitely could. We definitely could. We definitely could. We definitely could, yeah. We definitely could. Okay, so let's see. I mean, maybe we... Okay, what do you mean? Okay, like this? Okay, consistency models. What is this? Does this answer the question or something? Wait. Okay, describe this is one of the biggest most striking differences between most common consistency models that is acid and base. Okay, this define what acid and base stand for. Okay. Relation databases use acid models and NoSQL databases use base model. Okay. But that's not what it stands for. Clear advantage and disadvantage. This is not actually it, right? Oh wait, is this it? Wait, did I miss a question? Stand for. Okay, did I mean define it? Okay, stand for. I guess maybe they mean define it. I think maybe they mean define it as well. Okay, but stand for. So this is what it stands for. I think this is where they sort of show atomic consistent. They put base as well. Where's base? Oh, then they give us some ideas. Okay. Okay, question 1, define what acid and base stand for. So in this video, guys, do you see anything like stand for or... Okay, so this is used... Wait, this is a bit different. Wait, this is a bit different. Okay, so wait, there's more use cases? Okay, alright. Okay, so base consistency model... Oh my word! It's not. It's all in one. Like it's all in one. So the differences are. Oh, I see. Oh, I totally see now. Okay, so define what acid and base stand for. Okay, I can do that. So let's find the. Okay, so acid we know is atomic, right? We know that's right? It's just okay, so acid definition. So question 1. Acid stands for atomic. Oh wait, this they give you some bonus. There's some bonus material here, guys. Just always look for the bonus material. So atomic. Okay, all it stands for atomic, which means atomic means all operations in a transaction succeed or every operation is rolled back. What am I doing? All transactions in a operation succeed or they are rolled back. Okay, so that is atomic. Next we move on to atomic. I think atomic consistent on the completion of a transaction. Structural integrity of the data in the database is not compromised. Okay. So let's go back. Where's the atomic? This one is called. Oh, sorry. The next one is consistent. Oh, that's ironic, right? Because I didn't even write it correctly. Okay, whatever. I'll just write this like this: atomic, consistent. on completion on completion of a transaction the structural integrity is this right of the data the structural integrity of the data in the database is not compromised. The structural integrity of the data in database is not compromised. Okay, that is consistent, atomic, consistent, and then we have the first one, we have the second one, then we have this one, which is isolated transactions cannot compromise. So isolated transactions cannot compromise the integrity of other transactions by interacting with them while they're in process. Cannot compromise the integrity of other transactions by interacting with them while they progress. Okay, so this is, we have got to isolated. Let's move on to I think is the last one, durable, the data related to the completed transaction or persist. Next one is durable, the data related to the completed transaction, completed transaction will persist even in the case of, or persist even in the case of network or power outages. If a transaction fails, it will not impact the already changed data. Right, so that is asset. Okay, let's keep going. Acid indeed. All right, there we go. Okay, there we go. I'm debating whether to draw a line. Anyway, base stands for, has the same number of letters, exactly. Where is base? Base. here is base. Okay, base starts off with this. Basically available stands for basically available. Wait, is that it? The whole acronym stands for basically available. Basically available is B. Oh, basically available is B. Okay. Okay. Basically available. Okay. Basically available. Basically available. Okay. Basically available. Okay, basically available. Let's keep going. Rather than enforcing immediate consistency, base modeled NoSQL databases will ensure availability of data. Rather than enforcing immediate consistency, base modeled NoSQL databases. Oh, do we not do? Well, we haven't answered question 1 yet, so model databases will ensure availability of data. Excellent. So let's keep going. I think that's the first one. Now we move on to the next one, which is soft state. Don't have to be right consistent. Oh wait, did I miss something? I missed something. Oh, the bad real. Okay, so sorry. By spreading and replicating the nodes of the database cluster. By spreading and replicating the nodes of the database cluster. All right, let's keep going. I think that brings us to what's it? The next thing. Soft state. Soft state is the next one. Soft state. Sorry, soft state. Okay. And then for soft state, due to the lack of immediate consistency, data values may change over time. Due to lack of consistency, data values may change over time. Okay. Now, in the base model, data stores don't have to be right consistent nor do different. In the base model data, okay, wait. Oh, sorry, I missed this. This thing just disappeared. Okay. Oh, wait, I need this. What am I doing? Don't have to be right consistent nor do any replicas. Don't have to be right consistent nor do different replicas. Have to be consistent all the time. Oh, so this is still part of it? Okay. Okay, in the base model data, in the base model data, oh, I just missed it. In the base model data, okay, there we go. In the base model data, data stores do not have to be right consistent nor to different replicas. stores don't have to be consistent, nor do different replicas, Okay. There is one more, I think. Soft state, and I think there is eventually consistent. Okay, so then we have eventually consistent. Okay. We go. So it's B, it's A, it's S, and it's E. So it's eventually consistent. So what does that mean? The fact that okay, let's keep going. The fact that the base models do not enforce immediate consistency does not mean that it never achieves it. Okay, let's just finish. Let's just do it differently. It doesn't mean it never achieves it. However, until it does, data reads might be inconsistent. In the NoSQL database world, ACID transactions are less fashionable because some databases have loosened the requirements for immediate consistency. Okay, wait. Base models doesn't enforce immediate consistency. Doesn't mean it ever achieves it. However, until it does data reads might be inconsistent. Okay, so data reads might wait. Let's go back. What does it say? The fact that the data doesn't force me to consistency may eventually be achieved, but at what cost, guys? But at what cost? Consistency may eventually be achieved, but data reads may continue to be inaccurate, right? Okay. Alright, so this is base. I think we've covered base. I think I will be changing my study style for a little bit here, because I feel I could have done this a little bit better, and I feel like constantly just writing it out is just, it's not doing anyone any favors, to put it mildly. Guys, Okay, so this is acid and base. This is question 1. We are about to complete question 1. Alright, we're obviously going for the 3-question trifecta. So ACID stands for atomic. All transactions in operation succeed, they roll back. So basically, that's a stored procedure. You can use a stored procedure to reverse a SQL query, and you usually have you usually allow rollbacks if certain conditions in a transaction. So basically, rollback unless it's either all the rollbacks work or the transaction just fails outright. Consistent On completion of transaction, the structural integrity of the data in the database is not compromised. So everything is consistent. When one changes, the other changes. So you know it's a consistent set of events, isolated. Transactions cannot compromise the integrity of the transaction. The integrity of the transaction by interacting with them while they are in process. So you cannot create another transaction to influence that transaction. So basically they are isolated, they only occur in one place, and that is where the transaction occurs. Durable, the data is related to the completed transaction, will persist even in the case of networks or power outages. If a transaction fails, it will not impact the already changed data. So the data, on a distributed network, on a distributed network, but it's very easy to, it is always backed up, it is always ready, and it won't change because everything is there. Point of transactions, all this is there. So base stands for basically available. Rather than enforcing immediate consistency, base model NoSQL databases will ensure availability of data by spreading and replicating the nodes of the database cluster. Okay, so yeah, there'll be a cluster of servers, so it'll be available everywhere. So it's a distributed network. Okay, soft state. Due to the lack of consistency of data, the data values may change over time. In the base model, stores don't have to write consistent nor do different replicas. So the schemas don't have to actually be the same. Eventually consistency may eventually be achieved, but data reads may continue to be inaccurate. So this could change. All right, so basically that's what I'm going to do. I'm going to leave it like that for question 1. I'm not going to make some extra comments for this one. I feel like we're running low on time. Yeah, obviously we want to get to we want to get to challenges. Let's get to challenges. Okay, so here we go. So it's course 10 week 1 module 2. Are we still live, guys? Are we still live? I suppose I should check how long I've been live. I want to get to challenges. Let's get to challenges. Okay, so here we go. So course 10 on the learning summary. Let me just check. Okay, so we've already been doing 1 hour. Okay, so now we are going to do the use cases for ACID and base model systems. How are we going to do this? There was a certain way I did this. Use cases for ACID. Okay, wait, let's start off with, is it base? What do they start off with? ACID. Where's the use cases, guys? Where's the use cases? Find the use cases for me, guys. Use cases are here. Are they just saying financial institutions? Okay, so it's just use cases for financial. Okay. ACID. Okay, where there are many possible use cases. Okay, use cases for ACID. Okay. Use cases for ACID. Okay. Financial institutions, money transfers. Okay, let's keep going. Financial institutions, money transfers. Okay, one stands out. Financial institutions, okay, for money transfers, will almost exclusively use ACID databases for their money transfers. Since these operations depend on the atomic nature of ACID transactions, an interrupted transaction that is not immediately removed from the database can cause a lot of issues. Money could be debited from one account and due to an error, never credited to the other or not credited at all. Okay, so this is the use case. Okay, financial institutions, money transfers. Okay, so essentially, what are they saying? What are they saying, guys? Okay, so there was something they said that was like important, right? Let's say depending on the atomic, an interrupted transaction that is not immediately removed from the database can cause a lot of issues. Okay, so interrupted transaction, interrupted transaction, money debited instead of credited. Two short notes. I mean, it does make sense though. Financial institutions, money transfer, interrupted transaction, money debited instead of credited. So basically, if the transaction, you have to sort of say, okay. So it's a use case. So basically, if it's not credited, it's interrupted. So if it's interrupted, say the debit doesn't go through, but it's still on the system, then all of a sudden it goes through, and then they lose their money. Doesn't go through, stays on system, then money is incorrectly debited later on. Okay, so that is the use cases for ACID. I don't actually see or it is not credited at all. I think I'm just going to write down what I understand at this point. Okay, let's keep going. Right, I want you to understand exactly. It's just that simple. Okay, so where's so this is the end, right? Okay, so this is the end. So this is use cases for ACID. Oh, sorry, we're doing question 2. Okay, question 2, use cases for ACID. And I hope none of you are, drug users, because then you can just get the hell out of my channel, because obviously you guys are the sort of people that, pollute this world. All right, let's keep going. Financial institutions, money transfers, interrupted transaction, money debited instead of credited. Doesn't go through transaction on system, then money is incorrectly debited later on, or the money is not credited at all. Need to write that. Let's keep going. So let's go to some use cases based, dude. All right. Blah 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 blah. There should be a few. Okay, so a worldwide. Okay, so I'm assuming they're gonna say streaming, right? Well, not worldwide, but it can be used in a lot of specific cases. Okay. Worldwide online services. Online services. So use cases of base. These are as follows. So these are mainly for worldwide online services. Worldwide online services. Putting in capitals is a bad idea. Yeah, I've started to realize that. Users access to service. Users access to services. Okay, so I think this is reasonable. Increase well-known worldwide online services such as applications such as profile data storage. They need to be accessible at all times. Okay, so it needs to be accessible at all times. What else is there that I need to know? Okay, so accessible at all times. The system needs to be able to. Unavailable, the system needs to be able to. Okay, wait. Let's see. Common characteristics of the set, they need to be accessible at all times. Seamlessly to its video. Oh, sorry, wait. Stream. Okay, so need to be accessible at all times. Streaming e.g. Netflix, Spotify, Uber, and you also have, of course, the if part of system. So if part of system becomes unavailable, the system needs to what? Okay, if system, yeah, if part of system becomes unavailable, the request needs to be served on another request. Needs to be served on another server. On forms today, I don't know about that, guys. Let's keep going. Alright, so we've pretty much covered it, I would say. Yeah, use cases are pretty standard. Use cases are pretty standard, yeah. Yeah, I will say this, though. If I finish week 1 today, I think that's pretty good. I think that's pretty good. Like, we've been getting just quick better and better. Okay, so use cases for ACID. Financial institutions, money transferred. If it's an interrupted transaction, it's money is debited instead of credited, and it doesn't go through the transaction. Well, then the money could be incorrect debited later on, or it just could not be credited at all. So use cases for ACID is financial institutions. Use cases for base worldwide online services. User accesses. User accesses users access to services need to be accessible at all times. Streaming, Netflix, Spotify, Uber. So if the system becomes unavailable and a request is needed to be made, it needs to come through another server. Okay, so that's what we sort of know. So yeah, question 2 is sort of done. Can I summarize it without looking? Okay, so summarize that. Okay, so ACID you would get for financial institutions. You don't want the transaction to go through when it shouldn't go through, because then it can be debited instead of it's credited. So you want it to be atomic. For worldwide services, you always want them to be up and running, and you always want to be able to make a like if the system goes down, you want to be able to back up the system. Okay, let's keep going. I mean, yeah, that does sound right? Question 3. Okay, question 3 is describe the differences between ACID and base. Okay, well, first, I think we're going to put like a line down the middle of the page. 100% we're going to make a line down the middle of the page. So 15. It's about, I wish it was 18, to be fair. But, oh, did we lose just what happened? We lose OBS or something? What happened? Guys, what happened? Did we lose OBS? Did we lose OBS? What happened? It says we're still live, though. It says we're still live. Alright, good. It looks like we're still live, though, right? Alright, there we go. Alright, let's keep going. Alright, wait, that's not right. Okay, let's make it. Let's try again. So here, yeah, that mark I made previously was terrible, right, guys? It was terrible. Okay, so it's about 18 and a half. 18 and a half. Okay, so I'll just make it. I'll just do 9. Yeah. Oh wait, I hope that's enough. I really hope that's enough. Okay, so obviously we're going to be doing the, I don't know why that keeps happening. We're going to be doing the differences between, let's see. What are the differences between, let's see. Okay, so we have, okay, so we're going to do acid first. Acid, features, I guess? I don't know. Acid features and base features. Yeah, they totally were thinking of chemistry, totally. Okay, acid, okay, let's go to this one first. Do we just write it out? Should we? I don't know. Okay, here's the model. Should we say model? Because they say model here. Okay, let's say model. Say model, why not? Why not? Model makes sense as well. Okay. Here we go. Let's hopefully get it right. It's all about getting it right at the end of the day. So it's used by relational databases and it ensures transaction. Okay, so it's used by relational databases, so that would mean this relationship is primary key is columns and tables. Okay, there we go. Used by ACID model is used by relational databases. Okay, seems pretty key. Next, we have ensures performed transaction is always consistent. So what they mean by that is that one change in terms of data affects on another. Basically, integrity of data. There is no sort of fraud or anything. Okay, so ensures performs transaction ensures transaction is always consistent. All right, pretty gnarly. Used by financial institutions data warehousing. So it's used by financial institutions data warehousing. Data warehousing primarily is for online transactional processing, where they keep track of processes and the details of Snowflake schemas, and of course through financial institutions. Used by financial institutions and data warehouses. Pretty good, guys. I really haven't been interacting with my family enough for I don't know how long, so I really feel today I probably should spend some time with my family. That's why I want to finish this. Okay, so let's see. Databases that can handle many small simultaneous transactions. What are relational databases? Okay, so it can handle many small transactions, so it's detailed, so writing is very good. Can write data easily from any small transactions best with relational databases. Relational databases, which we discussed. Let's keep going. Fully consistent systems. So that means that the data integrity is ensured. Data integrity is ensured. Fully consistent system. One change of data in one table is reflected consistently in all other tables. Okay, let's keep going. I think that's all for acid. Let's go for some more. Let's wrap the base up, and here we go. So I think this wraps it up, right? Yeah, let's use cases. We did that. We did that. We did that. Okay, so this is it, right? Okay, so this is it, right? Okay. Okay, so base model, NoSQL, few requirements for immediate consistency, data freshness, and accuracy. Used for NoSQL databases. No real requirements for consistency, accuracy, and data freshness. I don't know what data freshness means, so I'm not going to write it. NoSQL benefits, availability, scale, and resilience. Okay, benefits include, okay, so it scales well, which means that it scales well means that lots of data can be put into it because it's distributed on many servers. Availability, if one server goes down, there's plenty of servers to make it up. And resilience, which basically is a combination of the two. So availability, scalability, and resilience. Okay, should I just write something? No, I think that's for the exam. Okay, let's go here. Used by the following marketing and service companies. So those are people who want to look at sentiment of customers and so on and so forth. Used by marketing and sentiment and analysis and customer sentiment companies. Was that wrong, guys? Was that wrong? Okay, social media apps. That could be Netflix, could be Spotify, could be Twitter, so on and so forth. Social media apps. Then we have worldwide online services, and those are the same as worldwide online services, which are the same as that. Okay, now we have NoSQL, favors availability over consistency of data. So we just wants to make sure that the data there's always some sort of data coming towards you. As long as you can get your data you request, that's all that matters. High availability, regarded of more importance than what is it? High availability is regarded of more importance than consistency. Okay, and then we have NoSQL databases used base consistency model. NoSQL databases use base consistency model. All right, so that is that. Okay. So am I meant to do like a summary of it or something? Okay, so am I meant to? Okay, I'll read through it and then I'll do a summary. Okay, ACID model used by relational databases ensures transactions are consistent. Used by financial institution data warehouses, writes data easily. How many from many small transactions. Best with relational databases, data integrity is fully consistent. One change of data, one table is reflected consistently in all other tables. Base model used for NoSQL databases. No real requirements for consistency. Accuracy. Benefits include availability, scalability, and resilience. Used by marketing and sentiment performance, social media apps, worldwide services, which is the same. As long as you can get your data you request, that's all that matters. High availability regarded as more important than consistency. NoSQL databases use the base consistent model. So ACID model used by financial institutions, use atomic transactions, use relational databases. Benefits include, benefits include you can have consistent data, it's consistent, it's all consistent. Such transactions are consistent. Base model, NoSQL is mainly used for it. It's high values, high availability, consistency, concurrency. It's has scalability and resilience. It's used by marketing. It's marketing, worldwide services, and the companies. As long as you can, yeah. So essentially, would I be able to do this in a test? I think so. I'm not sure. I don't know. I think so. I think I could do it. Anyway, let's keep going. Let's go to the summary. All right. Okay. This is the summary. Let's keep going. All right. So this is our summary. I'm not thinking enough. What do you mean, guys? What do you mean? That's pretty cool. Come on, guys. I'm trying to, I see all these things, but it's difficult. Okay, so in this video you learned that ACID and base are database consistency models. ACID and base, ACID and base are database consistency models. Okay. We also learned that ACID equals atomicity is consistency, isolated, durable. ACID equals atomicity, consistency, isolated, and durable. Okay. And next we have base, which is as follows. Basically available, soft state, and then eventually consistent. All right, that is pretty good. That is base, and then we have ACID RDBMS. It's focused on consistency. Then we have base NoSQL is focused on availability. NoSQL is focused on availability. Right, then we have usage selected by case-by-case basis selection. Usage selected by case-by-case selection. There we go. Pretty good, right? Case-by-case basis selection. Okay, pretty good. All right. I am doing a lot of writing, that is true. Okay, so acid and base with database consistency models, yeah. Atomic consistency, isolated, durable, yeah. Base, basically available, soft state, eventually consistent. Acid, ordinary is focused on consistency. Base NoSQL focused on availability. Usage selected by case basis selection. So atomicity, what is atomicity? Alter taxes. Okay, so if they don't, also sections will basically have to succeed, otherwise they roll back. Consistency, yeah, that's data integrity. Isolated means that any sort of transaction, if they run simultaneously, they can't affect each other, so there's no isolated incidents. Durable means that if something fails, it doesn't altogether fail. Base, basically available, so it uses basically available. So basically available means it's availability, scalable, doesn't have as much need. Soft state data is not always accurate, but the goal is just to send it to people. Eventually consistent, after a while it is consistent, but sometimes the data reading is not consistent. This is case by case basis. Okay, unfortunately it's gonna end. Okay. Been going for quite a while. It certainly doesn't feel like 4 hours. It's been 4 hours. 4 hours 50. Oh, so it has almost been 5 hours. Okay. Yeah, you put in 7 hours yesterday, and then you, yeah. Okay, let's continue. I am getting a bit fatigued. I must say, I'm getting a bit fatigued. To be honest, we all had a bit, so it's sort of messing with my head. Okay, distributed databases. Let's keep going. Distributed databases. You like what we've learned? I think there's different ways we could have learned it. Yeah, use cases I feel like we did very well in. The acid and base models I think we did very well in. Yeah, it's just unfortunate. So social media, how do they use it in social media? Well, they use it for streaming to put information. You just give the information. Sometimes it's not correct. Sometimes it misses. The goal is you give the information. Eventually it works. Okay. But overall, I would say for like this whole week, like the categories, like we looked at categories, also like looked at the NoSQL history. We looked at some introduction, and we looked at the history of NoSQL. We looked at common characteristics of NoSQL databases, and yeah, we talked about sharding. We talked about developer friendly because they can be deparsed, and yeah, very cool stuff. Questions or learning objectives. Okay, question 1 is, what is question 1 is, oh, you write out my understanding. I mean, that is an idea. That definitely is an idea. Okay, distributed databases. Okay, let's go to our learning objectives. How many are there? It's just 3. Oh, just 3. Okay, hang on. I just missed it. Wait for it to skip. Wait for it to skip. Okay, that's fine. Here. Okay. After watching this video, objectives, distributed databases, question learning objectives. After watching this video, you'll be able to describe the concepts of distributed systems. Describe the concepts of distributed systems. Okay, describe the concepts of distributed systems. Then define fragmentation and replication of data. Define fragmentation and replication of data. Question 3. Describe the advantages and challenges of distributed systems. Describe the advantages and challenges of distributed systems. Alright, so here we are, guys. Here we are once again doing the same thing we did last time, and here we are. Okay, so this is how long? It's a 5-hour 40-minute video. So describe the concepts of distributed systems. So this is basically fragmentation. So fragmentation is so fragmentation is this, and replication is this, then advantages of this, and challenges of this. And then they give us some bonus info. Okay. Pretty standard. Okay, so let's go to concepts of distributed systems. This is equivalent to looking at the slides, maybe, I don't know. Okay, here we go. It could be the equivalent. Okay, here we are. So, concepts of distributed systems. Distributed database, a collection of multiple interconnected databases. So should we draw a diagram, guys? Should we draw a diagram? Yeah, maybe we should draw a diagram. Why not? Question 1. Question 1, let's see. Yeah, the thing is I haven't really been with my family a lot because I just keep doing this. Yeah, obviously they don't really, but it's just sort of liveliness and spirit you need to bring, sort of boost the spirits, make everything better, essentially. Yeah, obviously I want to finish this, but okay, let's keep going. Describe the concepts of distributed systems. So first of all, let's draw our distributed system here. Draw a distributed system here, and here, and here, and here. Seoul. Okay, so we have Seoul. We have New York. And we have Berlin. And we have London. And data travels between them. Data is distributed between them, and Berlin and London is distributed between them in opposite directions, back and forth. Back and forth. Okay, so there we go. So distributed database is a collection of multiple interconnected systems. Okay. Distributed database is a collection of multiple interconnected databases. So that means, what does that mean, guys? What does that mean? Distributed database is a collection of multiple interconnected databases. It means all the databases are sort of joined together. What does it mean, guys? What does it mean? Databases. Okay, distributed system as a concept. Okay, so we have many databases at different locations interacting with one another. Alright, that sounds good, right, guys? Okay, what is the next one? Spread physically across various locations. Servers are spread physically across various locations. Okay, that's pretty fine. Fragmentation and replication. Fragmentation and replication of servers occur. So what is fragmenting? So you get replicated servers. Fragmenting, well, fragments mean, I think it's just the same as replication. Well, fragment is just a part of the server, and then they just stored together in a cluster, I guess, and scaled horizontally. All right, let's keep going. Is this right though? Is this just question 1? Or am I just insane? This is just oh wait, it's the base model. So that means uses the base model. So what does that mean? It uses the base model. So it's NoSQL. NoSQL uses a distributed system because of the servers. NoSQL uses a distributed system. Distributed systems are NoSQL. Use NoSQL databases in general. And what is it? And are thus using the base model. Okay, so that is using the base model. All right, so there we go. I feel like there's more though. I feel like there's more. There's no way, right? There's no way. Okay, okay, fine. So question 1 is done. Okay, so question 1 is distributed server, multiple locations. Servers are physically in the different locations, and since it's NoSQL, like data is on different servers, it can be horizontally scaled. It is used the base model. That is question 1. Let us keep going. All right. I feel like we're making some progress. There is another 5-minute video coming up. Yeah, obviously. Oh yeah, we didn't do the classic highlighting, the legendary highlighting, distributed databases, questions, and learning objectives. All right. Okay, let's keep going. All right. Okay, course. Define fragmentation and replication of data. So let's find fragmentation and replication of data. Okay, so what does it say? Yeah, okay. All right, hang on. To store a large piece of data on all the servers of a distributed system, you may need to break your data into smaller pieces. Okay, so now we're looking at question 2, fragmentation. All right, so fragmentation, it's pretty good. All right, let's see, fragmentation, all the servers into smaller pieces. All right, so into smaller pieces. Okay, fragmentation to break it into smaller pieces. Okay, so if you have lots of data on all the servers in the distributed system, okay, you have lots of data on your distributed system. If you have a large amount of data on your distributed system, on our distributed system, we may want to break the data into fragments. Okay, there we go. So we're breaking the data into fragments. Let's keep going. Suppose the base consists also of distributed, so we can break it into smaller pieces. Okay. You need to break it. This process known as fragment data is also called partitioning of data. Partitioning. Fragmentation is also called partitioning. Partitioning, a word we are all infinitely familiar with. Okay, let's keep. Oh, is the actual things here? Oh, we're just overreacting. Okay, let's keep going. A sharding of data. Oh, it's sharding. Wait, sharding as well. Or sharding as well. Fragmentation is also called sharding of data. Okay, so this is pretty good. Pretty happy with this, actually. No matter the name, all distributed systems need to expose a way to store a large chunk of data by key. Okay, so I need to expose a way to store a large chunk of data. So what does that mean, guys? Store a large chunk of data. Store a large chunk of data. Okay, so I don't actually think we need to add that. Okay, if you think about it, you don't really need to add that. Okay, so this process is usually done by the key of the key value record in two ways. Okay, all right, so okay, two ways key value. So partitioning, sharding, or fragmentation is typically. Oh wait. Okay, wait. Lexically. Okay, so from A to lexically means in order of the alphabet. Or the alphabet, okay. Arrow between A and C can be found on a specific server. Or by grouping all records that have the same key and pasting them on the same server. Okay, so grouping. So how do they want them? So you group all the records that have the same key. So that's like a family column or something, or family column, right? A family table. So I think they're talking about column-based, right? Column-based database, NoSQL databases. So for column-based NoSQL databases, you can group the records with the same key on the same server. I think that's okay. Okay, so you group the keys. Okay, same key you group. Okay, same key you group. or you group it alphabetically. Okay, either partitioned alphabetically, or by matching the same keys with one another. Yeah, we are definitely studying because that's not their words, right? Okay, so that's fragmentation. Pretty good. I'm happy with that. Fragmentation. Okay, fragmentation. Okay, I think maybe I've done this for too long, but I'm starting to lose my mind a bit, guys. It comes a point where it's just like, whoa. Okay, so we've got partitioning. Fragmentation. Now we have replication. There was one more. No, there wasn't one more. What's talking about? Data is now distributed. Oh, they want to show how it looks. Okay, so this is basically how it looks. You have your servers, I guess, or your databases, which are on servers. They don't really show the servers, but anyway, databases here, so they're all interconnected, and you shard, partition, or fragment data. Right, that's pretty gnarly. Let's keep going. So we have replicate. I think I'm gonna do this video and I'm gonna call it a day, guys, because I think we've done quite a lot of work today. I think 5 hours is enough. Yeah, I'm just saying 5 hours is enough. Yeah, 5 hours is enough. That's all I'm gonna say. Yeah, 5 hours is enough. I have to, and I did finish the course yesterday. How long will we stream for today, guys? 2 hours and 42 minutes. And 5 hours is enough. And learning summary. Let me just check that we're live. We've definitely done 5 hours. We've definitely done 5 hours, guys. 5 hours is, I think, pretty standard. I think it's okay. I think 5 hours is okay. So let's continue. Replication. All right. Replication is as follows: protection of data from node failure. Okay, so replication, protection of node failures. That's in case of a natural disaster. In case of natural disaster, data is backed up. Okay, stored on replication, stored on replicated partitions, increases availability. Okay, let's keep going. Data is now distributed to all the clusters now, but now how do we make sure that if a node fails, we don't lose all the data in that node? That is done through replication, where all fragments are stored redundantly in 2 or more sites. 2 or more sites. Okay. Stored in replicated partitions. Redundant data. All right, let's keep going. Redundantly in 2. Hence, in replication, systems maintain copies of data. Systems maintain copies of data. Replication increases the availability of data in different sites. Replication. Yeah, I said that. can be retrieved from another node, can record that is lost. However, if there's certain disadvantages as well, data needs to be constantly synchronized. Could lead to inconsistencies. Okay, so it could lead to inconsistencies. Consistency, synchronization of data, constantly being updated to a database can lead to inconsistencies. Disadvantage. All right, here we go. All right, let's keep going. Yeah, looking to finish. Yeah, exactly. Every site where the data is stored, replicated every service. Has to be replicated. Okay. Okay, so advantages of distributed systems. Finish this, guys. Is this called crashing or something? Like, am I just losing my mind? Am I just crashing? Partition fragmentation starting. If you have a large amount of data on your distributed system, we may want to break it into fragments. Fragmentation is also called partitioning. Fragmentation is also called sharding of data. Partitioning, sharding, or fragmentation, either partitioned alphabetically or by making the same keys with one another. Replication, in case of natural disaster, data is backed up. So that in case of server failure, you can go back to that server and make that the main server. Stored and replicated partitions, redundant data. Okay, so then you create the replicated, and that has to be updated when that data changes. Increases availability, because again, failure, you can go to another server. Synchronization, data consistency being updated, database can lead to inconsistencies. Disadvantages. Okay, so that means if you update, you constantly have to update with that one. If you update it incorrectly, it's incorrect for all of the updates. Okay. Question 2 is done. We have question 3 to do. Then we move on to okay. Question 3, the last question. Describe the advantages and distributed databases. Describe the advantages and challenges of distributed databases. Well, I think I'll have a break and then I'll see if I come back or not. We'll see. We will see. Okay, so let's go here. Okay. Advantages. Okay, let's write it like this. Advantages of distributed systems. Okay, reliability and availability. So it's always okay, reliability and availability. If server crashes, you can go to another backup server. Is there anything else you want me to say here? Okay, improved performance. No need to worry about conforming data to schema restrictions. Or data type restrictions. As far as I know. But anyway, saying something is better than saying nothing. Query process time reduced. Process time reduced. key relationships are direct and clear. Ease and growth and scale. Ease of growth, scale. And this would represent this represents ease of growth or scale. This is can handle very large amounts of data by, for example, sharding or partitioning the data across multiple servers. All right. Let's see. Let's see. What else is there? Continuous availability. Continuous availability. If there is crash, there is a crash of a server, you can use another one as the main server, hosting server, hosting the server of the databases. Okay, so that is the advantages of the distributed system. Fairly standard, pretty much what you would expect. Pretty much what you would expect, right, guys? So now we have the challenges of a distributed system. I can already tell you one of them, and that is consistency. Consistency when replicating data, large amounts of data through replication. All right, so that is obviously going to be one of them, but let's just go over it here. Oh, is there something I missed? Challenges of a distributed system. Bring availability, fast scaling, and global reach capabilities. Bring availability, fast scaling, and global reach capabilities. Bring availability, fast scaling, and global reach capabilities. Wait. No, sorry. I was wondering, how's that a challenge? Okay. Oh, wait, they're just going to deal with it. So writes and reads to a single node providing data that is synchronized in the background. So when data is write or writes to a single node. So when a database is getting reads or writes, the synchronizations could be displaced. Getting many reads, the synchronization incorrect data. Okay, run operations go to all nodes holding a fragment of data, reads to a subset of nodes per consistency. Writes go to all nodes. Hence problem if some incorrect data is given to even one node. Reads are done through subsets of nodes and not through all nodes. Okay, no transactions support or very limited. No transaction support, so that means basically you can't create tables, you can't create relationships. The relationships are not there. Very little support for events, transactions, and actions. And actions to transactions will very unlikely be easily accounted for. Okay, yeah, that's that. Usually like to do on one page, but oh well. Very little time during the day, I guess so. Okay, here we go. And I think that wraps that up. I mean, there's obviously this extra bonus thing. Not entirely sure what they're getting at with this. Okay, so advantage of a distributed system. I think we sort of know this. So improved performance because there's no schema restrictions. Queries can reduce because you have key relationships. Are very simple. Not many things. They're not very simple relationships. Unlike, of course, Snowflake schemas, ease of growth and scale. You can get lots of data and you can store it with continuous availability. It's if it crashes, you can go to the challenges of a distributed system. So just remember, just continuous availability. Yeah, I mean, I can just pull them out. Like I can just pull them out. It's just easy. Continuous consistency when replicating large amounts of data through replication. When a database is getting many read and writes, synchronizations could be incorrect data. Write to all nodes. There's a problem with getting to one node. Reads done through subsets data and through all nodes. Very little support or even of all of them to your database transactions like money will very easily be not accounted for. Okay, we have one more. I'm not really sure what they want to do here, but all right. So distributed database systems. What is it? Base model. Because they are primarily on the base model. Okay, so basically from the previous video, yes, we'll follow the base model, always follow the base model, always available systems. Yeah. Okay. Okay. So consistency may be achieved. However, definitely it is not achieved on a atomic level. Okay. So there's that. There we go. That is that. Right, now we move on to summary. Then I'm afraid I have to call it a day, guys, because yeah, I don't know. Maybe it's because I don't have my light on in my room, but this is just, hang on. I don't know. Summary: in this video you learned that. Okay, is that all? Okay, there's one more. Okay, let's just get rid of this. Okay, let's go here. Okay, there we go. So in this summary, in this video, you learned that distributed databases are physically distributed across sites by fragmenting and replicating data. Distributed databases are physically distributed across sites by fragmenting and partitioning data. Oh, so fragmenting and replicating data. Sorry, guys. Okay. Fragmentation enables storage of large pieces of data by breaking data into smaller pieces. Fragmentation enables storage of large pieces of data by breaking the data into smaller pieces. There's a whole lot of extra stuff I could say here, but I'm not going to. Replication means all data partitions are stored redundantly in 2 or more sites. Replication means that all data partitions are stored redundantly in 2 or more sites. If one node fails, data can be retrieved. Data be retrieved from another node. Distributed databases provide several advantages, but also have their disadvantages. Distributed databases provide several advantages, but also have their disadvantages. I need to get better lighting in this room. Distributed databases follow the base consistency model. All right, so in keeping with the theme of the work we've done today, I will go through it. Distributed databases are physically distributed across sites for fragmented data, so you can similar to sharding, you can create different versions of the data and put it on different servers, I guess, databases, and have different locations and link them all together. Fragmentation storage allows pieces of data, breaking the data into smaller pieces. Okay. Replication means that all data partitions are sharded redundantly in 2 or more sites, so the synchronization also occurs. Distributed databases provide several advantages, but also have their disadvantages. So I guess availability, scalability, and what was the other one? Yeah, availability, scalability, reliability, you could say. Simplicity, maybe. But definitely one of the disadvantages is consistency. Distributed database provides database systems for the base consistent model. And that basically means eventually the data gets consistent. Right. Thank you. I'll be back. I might be back today, but tomorrow we will hopefully have a new one. Hopefully I might not. We'll see. Okay. Let me just mark this off as done. Did it mark it off? Hang on. Yeah. I'll mark it off now. Play. Yeah. Okay, I think that covers everything. I suppose. Okay, well there you go. It says 5 hours. We've done this for 5 hours. We've been doing Coursera for 5 hours. Pretty nice. Don't know how long we've been streaming for. Could have been 6 hours. Might not have been. But if it's 6, did we stream for 6 hours? No, we didn't stream for 6 hours. What am I talking about? But yeah, I might come back for some more streaming. But for now, goodbye.